Hello, can you switch on the monitor? I am not able to see the monitor in the front. This monitor is not here, so I am not able to see my face. You can start recording, let the monitor work on its own. Okay? Monitor is not on. Oh, this and that is echoed, eh? Yeah, right, no problem. Power is there? Yeah. It has started. Somebody may have switched off the, yeah, I can start. Huh? Okay. I think we can remove the other thing. Huh? Right. Huh? Hello. Allow me to start and recapitulate a little of what I have taken from Remsburg's PDF notes. As I said, he is somebody who has worked widespread. Let me, I am sorry for mentioning it, but the treatment is both very thorough, meaning for every what you call several standard conditions, including combinations of various geometries, analytical solutions have been formulated and they are useful in case you want to write code or use it in a one-off instance, as in the case of aerospace applications. In the case of aerospace, at least in aero, some minimum quantities are there, maybe the quantities run into a few hundreds, including replacement spares. So, you can I have given you an instance of where you have a box used by aircraft people, where the sides have fins like this. There is a box and there is a fins, and then you insert the PCBs inside and ensure that they make contact with the outside. So, you see there two things are there. One is the contact interface, which is real. Then second thing is, main thing is by conduction, and you have a control on the pressure and you can do whatever you would like to do. So, the so called PCB card guide, printed circuit card guide, or any module which has contact can deal with it effectively. And I am saying, even if there is a small batch of maybe 200 or 300 aircraft, the stock of spares such that it can be maintained for 20 or 30 years. So, a large number is involved. In that case, it makes sense to experiment, find out, optimize and make your design. Coming back to the other applications, for example, if you are in armaments, you have made something which goes and I will use the word self-destruct instead of destructing someone else. Once it is deployed, it is lost. There is nothing like you are bringing it back and repairing it. And if you follow the news channels, you know, not all launches are successful, either armament or other way, and the extreme is probably space. While in principle you can go out and repair a spacecraft, it is not that easy. Things like normal communication satellites, and then a good example for us is the GPS system in orbit. They are expected to stay there for a very long time, and the conditions are different. You understood, no? There we have extreme radiation, not much of a chance for a medium outside to exchange the heat, like external surface does not have convection, and even internal surface you cannot afford to have much of a what do you call gaseous medium. I leave it at that point. The only thing is, all those formulations which have been given earlier by analytical methods are required in such extreme conditions. However, for the normal what do you call usage and things, still things are required. I am wearing, which is what is now fashionable. Some of you must have seen these activity trackers which have become extremely fashionable. It monitors, I don't know what all it monitors and whom all, it keeps a tab on how lazy I am. And then if you see inside, other than the normal band and this they have guaranteed that it is essentially waterproof. So, it is with all your watches, and there are even mobiles which are waterproof and front is scratch proof and everything. Whenever they say proof, you can know it is particular thing is there like that. And so, at the back we have this back rear surface has a tendency to get hot. So, various methods are used. So, what the designers do, you can now look at my screen. This is taken from another source, as I said, one Professor Schonholzer has come and worked with us. I have shown you earlier, but I will get back to you again. So, that much easier way of solving all this is somehow get yourself into an equivalent thermal resistance. At the starting point, a thermal resistance is very much valid, because normal laws of computing a network can easily be done. Now, it comes to other thing. Basically, here there is no heat build up or storage. So, two things which are very, very useful for us is probably this a simple resistor, and then I think you have already by now you have gone those things, and then down, this is what yesterday I referred to and I tried to get back to you. Aluminum has this beautiful nice number of watts per what you call meter degree centigrade of 229. As you go down, our phenolic and epoxy board, that is the GESC board we have, has very poor conductivity, nearly 1000 times lower. Further, if you go for still air, it is 10,000 times lower, and water is slightly better, maybe 500 times, and then even transformer oil and all that, conductivity is poor. So, the worked example here talks about, the next picture talks about saying, in case you have a block like this, how does it behave? It is very, very easy. Everything critically talks about this K of the material here. You understood, no? You have seen this K. So, for copper we have one number, and then for aluminum, you see copper has 150 comes here, and in the case of for aluminum we have this 229. So, this itself you know how things work, and if you come down, we come to the this what you call very low figure, which will gives you a very high thermal conductivity. So, you have a thermal resistance which is 1000 degrees centigrade per watt. The insertion of any insulation material into a heat flow path has to be planned with care. Even thin layers can lead to substantial increases of thermal resistance. Now, if you can relate what I showed you yesterday, you will see that the contact interface and the amount of pressure you apply across it seem to have a marked effect on it. So, in the other correlations which it is given in the what do you call the references at the back, something called asperity angle has been mentioned, saying if something can be approximated as small dome like thing, by pressure it will come down, especially if one of the materials is very soft, the other is relatively little harder. As you squeeze them, the pressure seems to increase the contact area. The moment you increase the contact area, you have this A will go up, and the moment the area goes up, thermal resistance comes down. You see here, thermal resistance comes down, and so on and so on, so on like that. So, we have a long list was mentioned there yesterday, if you remember, saying what all seems to have a difference. In that big list, temperature seems to have second order effect, not immediately. The external temperature does not seem to have a more threatening thing, I mean the other factors seem to have a more threatening thing than the simple temperature. And in this is a class notes prepared for our master students, you will see that same relations have been made here, saying in case there is a radial thing, as in you have a circular disc, you understood, no? This is a circular disc, and then this is the outside, and there is an external, what you call outer diameter, inner diameter and all that. For in the case of a radial heat flow, how things happen. And I have already shown you radial heat flow does not mean it needs to be just necessarily circular, infinitely large thing, as in a heat sink, which I showed you that HD 160 meant for high density. If you have a stud mounted diode in the middle, understand, no? Stud mounted diode, you turn the stud and then it clamps itself, you will end up with this sort of material which in the near area, depending on the temperature difference and all that, within, I expect within around 80 to 100 millimeters, the thing is essentially radial, and then there are graphical methods to compute how the isothermals are made and so on. And then of course, these are all for radial heat flow as per, I mean, a simplified equation. Similarly, in the case of a spherical heat flow, if you have a small point source, approximated point source, more than point source, it is a small disc like thing. In the case of spherical heat flow, see what has been written in there. It is just maybe please I mean be kind to me and the person has written. In case you are a professional, you are most compact, I mean most welcome to add to this. Much more complicated may escape analytical solution. Most practical applications of heat conduction electronic equipment can be approximated by formulas which are presented there. Now we come to a small explanation why I avoided again writing down a board or anything is, this being a video source, you can always come back, go backwards in time and try to read what is being written here. And if my accent is a little tough to get along with, you can always hit the mute button. Once heat has been conducted away from the source, it has to be transferred to a cooling medium. This can occur by convection or by radiation. In the case of natural convection, you have seen this P is a slug which is fitted to a flat plate, and the plate can be in different orientations. It is possible for us to keep it in the vertical thing such that the medium can flow on both sides. So, if you have something which is let us say typically commercial heat sinks, you have air, that is the cooling medium. But imagine you are in a other liquid, as in the case of underwater lighting used in lighting up a fountain, or you may have swimming pool sensors, then you have sensors which see biological oxygen demand, which are active sensors are in fact left in critical places, typically where pollution is suspected. In those cases, we have water which is ready to take care of the medium. In the extreme case, like let us have an agricultural sensor, you can have widely varying medium. When things are dry, probably you end up with dry air which is a very good insulator, and when something gets wet, things are slightly different, and when something gets waterlogged, from the thermal point of view it is convenient, but from the sealing IP index of protection point of view, they are not good. So, in one of the early lectures I have shown you where we have buried some sensors for agricultural monitoring. So, if you take any plant, we all are familiar with modeling of a full crop. Crop can be modeled easily. Similarly, there are plant modeling. Plant modeling is also possible. Now, we come to what is called root activity. So, just near the ground, just above the ground, there is certain amount of activity, just below the ground certain activity, and deep down our commercial food crops where you grow basic what you call yearly or very seasonal crops, very little effect is there below maybe a meter down. Again my opinion, but you kindly, I stand corrected, you look it up about it, and the maximum amount seems to be from just above, let us say 5 centimeters above down to about 30 centimeters. In all these places these devices are mounted, and invariably if you have a device it needs some powering up. It is very convenient if we just have only maybe something like a 3-wire communication by which you can get data as well as power onto these modules, which will end up with having some amount of heating and power conditioning at the bottom. So, in those cases we end up with, if you look at my presentation, we end up with this convection. Unlike in the case of conduction, this positional change and so on, no, convection by cooling is the most common. So, this all I think said it again and again. So, we have removal by convection. Air is by itself a very poor heat conductor. It removes heat when sticking over a hot plate. The heat power is conducted to the cooling fin and so on, there it is transferred to the air. Here we come to several combinations of where things can move. So, if you have a top surface, cool air gets drawn and then goes up, and then this this arrow here is about the power being put in, it is not the airflow. So, the power is given here, and then this cooling seems to be very convenient. And in the case of bottom surface, we still have a problem, a little bit of what you call the voids or pockets form here which prevent air from being circulated. And then you have this normal vertical orientation and multiple fins. Where these are useful is, imagine you have a enclosure which is carrying all the heat. So, you have a top surface in which some heat is lost, you have the bottom surface. If it is elevated, usually you have the rubber feet, cooling can take place, and then extreme left and right surfaces where these things can be improved. Now comes to the other thing, is there a way for us to increase the surface area? So, we come into this for the surface area, we come into this beautiful thing about saying, why do not we just put more and more fins? Okay. So, if you put more and more fins, obviously more area is available, and then why not put grooves along the fins, which I told you in the case of a commercial thing, how to make the grooves. If you have to depend only on natural convection, it does help a little. In fact, probably it helps a lot. So, here for the purposes of completion, they have given saying how to determine this heat transfer coefficient. We know how much is the power, and then if you know the amount of power, we can get a delta fin to ambient. Conversely, if you can specify this what you call fin to ambient, you can show what is the maximum power it is there. As we go down, good approximation for the convection coefficient is given by the empirical formula, where for cooling a vertical plate it is 1.3, this one alpha has been introduced here, where h is height of plate, a top sided cooling, it is this length into width by this, and here there is a small, what do you call, I will call it a, long ago we did not have a back button. You can never undo things which you have done. Maybe that is the reason why things made in 1800 are still valid, because it was made. Nothing like, no, I will correct it tomorrow. It is not like a social networking where it really does not matter. But this is the original what you call draft copy which I managed to get. So, alpha in the case of bottom sided cooling comes to 0.6. Now, if you ask me how all these numbers came, they are all empirical. I mean, somebody has put, and in fact we had that plate, a small plate on which a small, it was taken, I know, for some convenience, 150 mm by 150 mm plate square, and in one variant keeping the total area same, 150 it will give you 225. In another variant, one side was reduced to 100, other side was made 22, and a small TO3 transistor was mounted, and it was made to dissipate heat by keeping it in the linear region. So, there was a large current flowing, and there is a voltage drop, and the transistor was getting heated, and at the base of the device we had resistors, and the base drive could be controlled to ensure that the amount of wattage we control. So, these have been formulated. So, is here for a square plate obviously H is same, but in the case of a rectangular plate we have it length into width by length plus width, and so on and so on. No? We in the end we have come to this interesting thing, saying in the case of multiple vertical fins, the equation can be applied to a fin spacing of about this much, depending on the this alpha. For still smaller spacing, the airflow gets choked sufficient to reduced cooling effect. This is by example, by actually running things, meaning as I have given an example of a plate which is a 150 mm by 150 mm, and they have kept very close using some spacers, that is phenolic rod was taken. Imagine this, the phenolic rod, and then slits were cut, and then they were kept in a way airflow does not what do you call get affected. So, the if this were a plate, no, so we have these fins which hold the plates together, two in the side top and then one in the middle, so that the spacing is maintained, and then they were also made very thin, so that in the normal case they do not impede the airflow. Then what has been found out is that if you make them close, nothing can, what do you call it, really does not help. So, we have a worked out example is given here, saying for a horizontal surface, okay, calculate for a vertical, calculate for the following plate the heat transferred by convection when already directly the differential between the ambient and the surface of the heat sink is given, saying it is around 40 degrees, which is typically what is likely to happen. In the standard temperature conditions we have 25 degrees. So, the plate can be at 65 degrees, but generally it is a little elevated temperature. Imagine the ambient is 55, the plate can still be at 95 degrees centigrade, which is not a impossible condition. So, things have been calculated, saying in the case of it is in the vertical conditions we have 10 watts. Okay. And in the case you kept it in the horizontal condition, you have seen this is 0.3. We have 1.3 for the that alpha 1.3 for the top side conduction, then we have 0.6 for the bottom side condition. So, we have approximately 6 plus 2.7, around 8.8 watts can be dissipated when it is in the vertical condition as compared to 10 watts when it is kept in the vertical. So, in the horizontal condition, no, there is a little degradation. Vertical plate cools better than a horizontal one, as the convection efficiency depends on the density of the air. It will decrease with increasing elevation. So, this I think it keeps on evolving. So, for this slide at this point, no, just accept it, saying the heat transfer coefficient at sea level will, if you take it as 100, and this is kilometers, at about maybe 5 kilometers you still have a 4 kilometers to 5 kilometers you still have, most of it can be done. Further, if you go down, go up to 10 kilometers and all, the air cooling naturally does not occur. It is unlikely that we ever use things at this large altitude meant for normal natural air convection. At this point, we come to why not have turbulent and forced convection. To make it very, very simple, this whole thing has been put in a small graph. When the movement of air is forced by some mechanical means such as a fan, heat transfer is greatly improved. Its calculation becomes involved. Why it is mentioned that the calculation becomes involved? Because it is dependent on whether the flow is laminar or turbulent, which in turn depends on the geometry and the surface condition of the surface. Okay. Read it for yourself. Velocities beyond 6 meters per second do not seem to bring any significant improvement. This is also an observation. Okay. This also is clearly a simple observation. For purposes of completing, we have a radiating plate, radiation being shown here. Any heated body radiates electromagnetic waves, which is infrared, shown. This flux aids in cooling the body. The radiated power has been shown here, but again I will take it with huge amount of temperature difference, radiation coefficient. You have seen there is a small, what do you call, catch in it. The what do you call, temperature and these things are interdependent on each other. So, we have surface temperature and so on, and we have this beautiful thing called shielding factor. If they are spaced very close together, one fin shadows the other. So, the shielding factor becomes very, very bad. For showing important things here, this is where I kept on stressing from other things. Permit me one more time to talk about emissivity. Polished aluminum reflects away all the heat. Same thing happens with polished copper. Since there is both of them, commercial aluminum and commercial copper polished, because its worst condition are very good reflectors of heat. So, I have given you an example of the toaster also, the bread toaster. If you look inside, you can see the heaters which radiate everything, and outside where you touch, you do not feel much of a heat, because just underneath that is a aluminum reflector on both sides. aluminum reflector avoids all this, and then by very carefully spacing and then also ensuring that there are no radiant coils on the outside, they manage it well, and all you need to do is maybe put a slice of bread and push it down, and whole thing miraculously comes. Depending on how miraculous you are feeling, sometimes it comes charred, but it is still okay. And you would notice one more very interesting thing in it. Interesting patterns are created on the toast by masking part of it inside. That mask itself can be made of any material. Aluminum is about best. So, on the bread, if you keep a, let us say, a heart shaped any aluminum foil, and if there is a way of you to hold it, do not try it and short circuit the thing. When you take it out, you will find a beautiful toast with a heart shape. I am sure if you have seen in the movies, all sorts of gimmicks are used for this. Now, looking back at this here, most of the thing here, anodized aluminum emissivity is shown as 0.8, and next comes the interesting thing here. Can you see this? Any color thing seems to be, any color seems to be the operating definition. Now, you can go back to what you call the handbooks, and the truth is these numbers are all correct, 0.8 to 0.95 are correct. Do not go to blogs where the people copy posters, copy something else from somewhere, and then by what you call, I do not know, it is a devil's work or what work. No, these days drag and drop, cut and paste, copy and paste is there. So, somewhere somebody has written saying black is better in some other context maybe, and then maybe equal opportunity and maybe other things. That apart, in the case of our radiation, it does not make a difference if you make a heat sink black or not. Understand? Only thing is it should not be polished, and if it is dull, it continues to have this 0.8. And paint and all have still a problem. It is not that easy to make flat enamel, means what you are likely to find in optical equipment. It is a paint which adheres closely to the surface, and from it prevents reflection. So, it seems to be absorbing most of the radiation, and in the same condition it also emits all the radiation. So, if your surface plate is high, as in the case of, imagine you have resistors, wire wound resistor and all, which are encased, and often they are dipped in a ceramic material. They radiate, resistor reaching around 150-200 degrees centigrade is common, and they radiate, and this radiation can be picked up by your sensitive small equipment, especially if you have a radial heat spreader. You have seen that, no? The word, it is generally made of beryllium copper, it nicely sits snugly on a TO5 can. So, I have this TO5 can, and then you have this heat what you call spreader, which has radial fins all around. If you have such a thing very close to a heat emitting high temperature what do you call thing like a resistor or other, occasionally it may be difficult for we to understand. No, they even use heaters inside the equipment. I have told you about the oven controlled crystals. So, you have a heater on the outside. Some anywhere, no, they have a tendency to pick up heat from outside. It does not radiate. Then we come to the last point saying rolled sheet steel. Rolled sheet steel is usually what we keep using the word sheet metal everywhere. The correct technical word is a steel which is hot rolled. This is what you get everywhere, in which you use it for boxes and all that. It looks like same thing appears there also. and you can improve it slightly by, this is in the as rolled condition, it has a dull grey. You can improve it by putting it with this flat paint, which I do not know, so sometimes at least here locally they call it blackboard paint, and then the thing which is used inside. Next picture shows you shielding factors for different spacing. So, you have B by C, you have seen that now B is very long compared to C, then A by C, that is A you have here, that is the height of it versus C, because this is the one, if radiation comes, it hits this point and then it goes here. Let me see if this works. So, you have radiation which comes here, it comes here and it absorbs. If below this, the chances of any radiation hitting here is small, and if this is a very good absorber, obviously it cannot give you a total internal reflection. So, you end up with only this small area and a little in the end what you see here contributing to radiation being useful. So, as you see, as the depth keeps increasing, we have this, you can see how well this factor gets worse. Seen this here, phi, shielding factor owing to neighboring plates. As the depth keeps increasing, the shielding factor keeps increasing and becomes very high. You see here it comes all the way to 0.8. So, of the total surface as counted for the convection, only 20% of is available for you for the radiation, and that coupled with the very poor temperature difference will not permit you to depict things. Calculated the radiated power for the plate, calculate the radiated power, several of these are mounted, delta FA is maintained. So, total, if you attach all those things and all that, you get a figure of around 6 watts, you understood. So, the plate shielding factor is 4 because of the depths. Using this equation, what all is there, in the end, comparing these results with one finds that for the unshielded case more heat is radiated than convected. Shielding case reduces the radiated power, then convection becomes a major factor. Above calculation show the effect of shielding and the radiated power, and mind you, what is shown here as the various the emissivity and those things are still, he has taken the best emissivity here, you understand, 0.85, which is not really true in most of the cases. So, when he calculated including this emissivity and so on this thing, using these values, power turns out to be for the above configuration. But again, it is only to illustrate a simple example to be worked out on a board for the students. This has been done. My own practical thing is you have to be little careful about it. So, we have beautiful fin effectiveness and how well calculate the total power for the example and so on. We have, this is the figure, you have this 1.72 degrees centigrade per watt has come about. Why this figure is being given is commercial offerings in the market, they would have done all this and then give you, saying if you have a stack of plates or an ordinary plate, and then if you make things, how well they match up. We come back to, In the earlier chapter, you remember there were pin fins which are having a small square cross section, and then there were fins with a parabolic. Parabolic means the fin is shaped like this. Okay, then you have the other one inverse like this, no, saying it is something which is a tapered pin. Why that is all done is we have a regular issue in the way the temperature of the surface changes. At the point where the heat enters by conduction, you see we have T1 at that point, and the bottom you have T3 and the top we have T2 due to conduction, and all along slowly convection is trying to cool the plate. So, air moves from top to bottom, it heats up, therefore, its cooling effect is smaller at the top than at the bottom, which is a very, very important thing. Along the heat path source strip, power is being convected and radiated. The power density becomes steadily smaller. This heat spreading process is, again, sorry for reading it again. Here he says it cannot be, what he means is too complicated to formulation in a closed expression. In one lone instance it can be done, but you cannot make a generalized thing for all known things. So, as we go, somebody has done this this thing, the how the efficiency, this is by practice. So, we have as the what do you call RTHC, thermal resistance to the fin tip, assuming no heat is being transferred by convection, and thermal resistant fin to ambient, assuming entire fin is at uniform temperature. So, we have, depending on this relationship, no, the efficiency keeps coming down. So, while the flow is what you call, my flow has been good, I will just about stop here, so that I will deal with it later. Calculate the effectiveness of the aluminum fin as shown in the figure. He has given ambient of 70 degrees and I am sorry, the source is 70 degrees and the ambient is 30, and we have this 20 by 12 effects. So, the convection solution gives you conduction resistance and then the efficiency to 0.48, but you see here the actual thermal resistance becomes this thing, but a lot of it depends on efficiency here, which you understood, no? We have read from a table. Neglecting heat spreading, one has found the example, and then if you include what do you call fins of this great length should be made much thicker, or their effectiveness will be significantly reduced by heat spreading. I will repeat it again, and from here onwards we end up with the capacitive part of it, which is, at least in my domain or expertise, only if you are a semiconductor person working with known what you call power dissipation and all that, are more for the making the analysis complete. So, we have slug and how long does it take and so on, and then we have the equivalent circuits and how these things work. So, thank you. I will stop here. The equivalent circuits and dealing with it, I will see how best I can take it up. So, thank you. So, thank you. I will continue this lecture in the subsequent lectures, because that is something which is best dealt separately. So far what I have talked to you is about how in a simple way we can calculate if a plate, standard plate is taken and so on, and if you already have some equivalent relationship by which the efficiency or fin effectiveness versus those things are all known. As a close approximation has been presented here, and real life things are a little slightly different. Okay. We will continue next time. Thank you.